Dearly Father, we thank you for this day. And Lord, thank you for these students. And I just ask you to bless this class today, Lord. In your name I pray. Amen. So what I figured I'd do today, light switches. That's right. I sometimes forget this is like, one of those rooms with light switches. It's very exciting, really. It's like buttons on a cell phone. It's just very satisfying. So analog and just, such a finality. Just like that. It's amazing. That's not analog? Light switches are very digital. Yeah. Right. I wonder if the meaning of analog and digital has been corrupted by recent technology. Let's see here. Maybe. So this is, of course, the wonderful PDF brought to us by Professor Keith Conrad of UConn, who has tons of these posted on his website, his blurbs, as they're known. And like I told you guys, he's about 5 of them, just on Galois theory. And so we've looked at his previous one, the Galois correspondence, a little bit. This one is just what it sounds like, some examples of the Galois correspondence. And so let's see here. I think it's useful to look. Actually, we've already looked at this one. I did not use I think in Dummett and Foote he uses what? Is it rho that we wrote last time for this one? Yep. But rho is, omega is a third root of unity. That's part of the field diagram, the lattice diagram, field diagram for that. But if you read through the, logic here, it's probably helpful to just make sure you've got all your, thoughts in order in terms of figuring things out. But that said, I'm going to go on to the next one because we've already talked about this one. The next one in here is perhaps relevant to other parts of your existence. Right? Like I think this is one of your homework problems, right? You don't know. Okay, yeah. I'm pretty sure it is. If it's not exactly your homework problem, there's something very close to it. You're like, so why on earth would you assign something that's so publicly known as a homework problem? Because I think it's healthy for you to think through this example. But my point is, you're not alone. You can look at this and work through line by line. That's kind of the point of the homework problem, all right? What's interesting here, of course, is that, let's see here, x to the fourth minus 2, that factors into x squared plus 2 times x squared minus 2, right? X squared minus 2 factors then into x plus root 2. I'm sorry. Did I say, I meant root 2. I've had this problem. I'm suggesting to you that the square root of 2 is 2, which is not usually true, right? Is there any context where that's true? Mod 3, okay. Is there a context in which the square root of 2 is 2? Interesting question. But maybe it's not that interesting. Let's see here. Continue, but I'm intrigued. What's going on?
Just
Just
unnecessary stuff.
It's fine. I'm curious.
Square root of 2 is 2 in mod 2 because it's 0.
Square root of mod 2. Yeah, it's characteristic too is where everything false becomes true, right? Stupid characteristic too. Anyway, like for example, the stuff my brother does. Well, he's kind of in the infinite dimensional analog of that, but he studies these vertex operator algebras, and at the base of all that is the representation theory of Lie algebras. All right. So back in the late 19th century, we understood something called a semi-simple. A semi-simple Lie algebra is basically one which can be written as a direct sum of simple Lie algebras. So then the question becomes, how do you classify Lie algebras of a semi-simple type? Right. So the classification of Lie algebras, like semi-simple Lie algebras, there's like these 5 infinite families or something like that, and there's, I don't know, some number of exceptional cases. This stuff was all done by a lot of it by Sophus Lie, some of it by Lie, and then I think who finished it up? There's another. Yeah, Killing is the one who really just really did it. Filled in, didn't miss things. So yeah, that's about 100 130, 120 years old, something like that. But then, I was getting to a point here. Maybe in the last, maybe about 40 years ago, maybe 50 years ago, people started thinking about, that's all over characteristic 0, right? So what if you study Lie algebras over fields of finite characteristic? How does that go, right? So like some of the giants in the field of Lie theory right now kind of made their career on settling some of those questions over, say, characteristic 4, 5. So it's kind of like, they've done, I think they've done all the characteristics past, I forget what it was, maybe past 3 at this point. I'm not sure about 3. But I think past 4 or 5, I mean, well, 4 is not a characteristic, right? So you should probably call my history. That history you would expect from a historian of science, but it's not history you should get from any practicing math teacher, right? If a math teacher tells you something about a characteristic 4 field, you should be very worried. Yes. Oh, you're not worried?
I might think of the ring.
You might-
It's not integral domain with characteristic 4.
Oh, he's like, you just,
C4 or something.
so you don't dispute the characteristic 4, you dispute the term field.
Yeah.
I like that. That's a healthier way to be.
But I still like.
That's optimistic. It's very optimistic. You're like, there are characteristic 4 things.
No,
They're
but
just not fields.
I still not optimistic about that.
Oh, but yeah.
I mean, rings
Right. Yes, we have learned that rings
Are not enough to
are not such a simple thing. Yeah. We like to find simple ones. So, it's horrible use of common terms and technical meanings. It's
I mean,
anyway.
there is no classification. I think.
Yeah, we're having trouble with that. The analog of the Jordan form. Yeah. Whatever that is, I don't know. But oh, okay. Getting back to my story. So up to characteristic 5, and I think even characteristic 3, maybe in the 1970s, those sort of analogous calculations that Lie did over characteristic 0 and killing early 20th century. And then there's characteristic 2. And there's just no hope, apparently. Like, it's just every different concept that is separate, and these separate concepts are used to build theorems in higher characteristic. A lot of these things become the same thing in characteristic 2. So like sorting through that classification theorem in characteristic 2 just becomes quite awful. So anyway, I am mostly a characteristic 0 sort of person. So I don't really know much about these things. But it intrigues me that people have spent their PhD, they spent their graduate days and then postdoc days and so forth just in sorting through characteristic whatever questions. It's interesting. All right, so, but here, the 4th root of 2 adjoin I, that is a splitting field for x to the 4th minus 2, which means we know it's a Galois extension over Q, right? And furthermore, the central point, if you read through these PDFs, these calculations of Conrad, and also Dummett and Foote, of course, is that basically the automorphisms are fixed by what they do to a set of generators for the field, essentially. I mean, the 4th root of 2 and I, products of those, right, build anything in the extension field. So what happens under a Q-fixing automorphism? I mean, there's only Q-fixing automorphisms because Q is the prime subfield. But what the automorphism does to the 4th root of 2 and I pretty much fixes the automorphism, right? So if you think about that, and you can't send the 4th root of 2 to I, and you can't send I to the 4th root of 2 or any of its, or any of the other corresponding zeros to the minimal polynomial of the 4th root of 2 or the I, because then you would violate, you get a contradiction because they satisfy different algebraic properties, and the automorphism has to preserve algebraic properties. So if you don't preserve algebraic properties, you're in trouble. But he has an explicit, for example, he's like, you can't send, and there's more though. He points out you can't send, let's see here. He says you could send this to this, right? Or you can't. Oh no, I missed a very important word. No. Yes, thank you. I'm sure I would have figured that out as soon as I got to the next line, but I appreciate jumping in. So they don't respect the algebraic relation x plus y, which holds for what? Oh, I see. Because this plus that is 0, right? I couldn't send this to that and this to that because this plus that in the image of the hypothetical automorphism is not 0. So if things sum to 0, I must map their images such that the image is also summed to 0. It's kind of like a next level consideration. We've mostly just focused on sending things that sort of have the same order to objects of the same order, right? Here, this is actually sending this, that's fourth order, right? What do I mean fourth order? I mean the minimal polynomial is order 4, right? Yeah. And this is also this is also something that if I raise to the 4th power is rational, right? So they're both kind of the same kind of objects, but yet they don't respect this x plus y being 0 and being mapping to the image of x plus the image of y being 0. So, and the organization that he uses in here is also kind of nice, right? He says, okay, so if you want to think about an automorphism in the Galois group of Q adjoining the 4th root of 2 and I, the question is, what does it do to all 4th roots of 2? Well, excuse me, he says, don't think about it in terms of what it does to all the 4th roots of 2. Instead, what do you want to do? Think about what it does to just the 4th root of 2 and I, not all of them. And he says, basically, that you can build all of the automorphisms, if you think about it, by just looking at this R and S, where R is the one, and we kind of did this before with other examples, right? Our sigma and tau that we built the S3 from was based on fixing one of the generators and moving the other in the kind of the most natural way. So here, he sends that to I, right? And that's going to be okay. Like, that's a reasonable thing to do, because if you think about the minus this, right? It sends it to minus I. And so the sum of x plus y is 0 still. That consideration is fixed. But that's actually this idea that you have to worry about x plus y being 0, that's actually very, very helpful if you start thinking about it. It eliminates a lot of possibilities that you might otherwise worry about.
But the thing that you just said was actually working in the opposite direction.
Uh-oh.
He said that it works because we know that it maps the negative of that to the negative, which is just using the property that we're assuming that the images are going to map to 0, and then you use that to deduce what the negative must map to.
Right. Yeah. Well, what I'm mostly saying is he doesn't worry about, the 4th root of 2 mapping to, say, let's see here.
So the problem is the thing he says above is that he gives 2 different explicit mappings for the 4th root of 2 and the negative of the 4th root of 2.
Yeah.
What we're doing here is we give just a mapping for the 4th root of 2 and just a mapping for the negative.
Right. That is fair, yeah. So he fixes I with R, and he fixes the 4th root of 2 with S, and he moves I with S, right, to the other, x squared plus 1 factors into x plus I times x minus I. Those are the, yeah. So both I and minus I take minimal polynomial x squared plus 1 over Q. And then he just looks at these, you've got the identity, R squared, R cubed, and then these guys, right? And I think, I'm trying to remember here, I want to say that the S, the RS, the R squared S, and the R cubed S, those are all, I think those are all order 2. Like if you look at S squared, S composed with S, what happens to that? Right. Oh, yeah, so S, you map I to I, but what about that? Oh, it's fixed, right? I'm sorry, I don't know how to read my stupid table, right? It's fixed. So that goes to that, this goes to minus I, but then it goes back to I again. So yes, you're right, we fixed both elements, so S squared is the identity. How about this one? Yeah, I think I better write that down, right? Oh, no. Now we can't see it. So we're looking at sigma equal to RS, right? Where RS does what? It moves the fourth root of 2 to I times the fourth root of 2. Is that right? And RS does what to I? Minus I. And so we wanted to look at RS squared. We're good on the I, so we've got to worry about the fourth root of 2, right? Let's see, so that goes to, oh, but I do have to pay attention to the I too, right? Which is minus I times I fourth root of 2, which is the fourth root of 2. So yes, RS squared is the identity. And so if you sort through that, in fact, all of the last 4 things in the table square to the identity. So you have 4 elements of order 2, well, excuse me, 5, because R squared also has order 2. And in fact, R to the 4th is the identity, right? Which you can see from this, right? Because you send sigma to the 4th of I does what? Sigma to the 4th of I goes sigma cubed of I, which then is what? Oh, I'm sorry. I need to look at that one. There's nothing to see here, is there? I'm an idiot. Like I's just fixed under the powers of R. So R to the 4th acting on the 4th root of 2 is more interesting. R to the 4th on the 4th root of 2. Oh, I'm getting very confused. Why? What am I doing? I'm looking at the identity column. Maybe you should find another teacher at 8:15 on Monday, Wednesday, Friday. I don't know, but this is all your fault, Sam. It's here. Yeah, it's hilarious. It's a hoot. Let's see here. So we look at R to the 4th on the 4th root of 2. We get R cubed on I, the 4th root of 2, right? The I gets sent, that's just I times R of the 4th root of 2 again, which is I, so we get an I squared, so we get minus, so it becomes R squared times minus the 4th root of 2, right? And you just keep going through the powers. Eventually you get back to the 4th power fixes both that and that. So the 4th power of R is the identity. Anyway, so you can start to see what the Galois group is here, right? But there's arguments up here which are really useful, right? Which is that the degree of the extension is 8, right? And if you think about it, we can send the 4th roots to there are 4 choices where to send the 4th root of 2. There's 2 choices where to send I. And that gives us 2 times 4, which is 8 possible automorphisms. And they must all actually be automorphisms because the degree of the extension is 8. It's a splitting field, so it's Galois. So the size of the Galois group has to match the size of the extension by one of our fundamental theorems, right? And this is their explicit arithmetic, right, which you guys should work through for yourself. That's a homework problem, actually. Sorry to talk about your homework. And now here he talks about sort of, further nuances of it. For example, it's apparently D4 because you can also prove that RS is equal to SR inverse. So the interplay between R and S is exactly what we want for the dihedral group of, however you want to say it. It's technically order 8, but it's the D4. And he says some things in here that might kind of catch you off guard. He's like, it is not equal to D4. It's just isomorphic, right? And so, fair enough. The automorphisms here are not actually defined on. So I don't know. So this begs the question of how Conrad defines D4, which I'm not sure.
In the set theory example.
Yeah.
In type theory, you can set things up so that isomorphic things are going to naturally be
Ah. Yes, so you're saying elevate sameness to equality in the proper philosophical background, yeah. But, technically, these are not really rotations on some square or something, right? They're particular automorphisms of that bizarro extension field of the rational. But anyway, he eventually, of course, writes down the diagrams here, I think. Here they are. Oh, man, he doesn't ever draw the diagrams. Well, I guess that's up for you guys. I think the diagrams are elsewhere, but let's see here. So these examples are kind of nice because he actually, he puts down, he'll give you like this, the subgroup, the lattice of subgroups, and then he starts the field diagram, right? And he kind of traces through the logic of what has to go there. How do you figure out what goes here, here, and here? And he actually, kind of goes systematically, step by step, to explain why we put those things there. And I've done some of that last class, but I think this is a great supplement to my lecture. If you read through this, you'll understand things much more deeply, and you might actually find solutions to a couple of your homework problems while you're at it. So, yeah.
Do we draw the diagrams like that so that the length, the height of those lines is kind of proportional to the degree of the extension? Is that why we do that?
Oh, is the length of the line proportional to the degree of the extension? I don't think you can make that go for more complicated diagrams, just because of the trigonometry and so forth involved. At least not with respect to Euclidean notion of length. Yeah, because this is a degree 2 extension. What's the degree of this over that? 3? Oh, that's also 3? Curses, your observation is at least true for this one. Ah.
I'm just wondering, because when we first got to it, it was like there were different layers and I didn't understand why. But then that kind of...
I think it's, for my limited understanding is mostly just that the length of them are for the sake of the diagram being beautiful and readable and separating symbols. But I think if you just think about the degree extensions, if you think about degree extensions, if it's 6 to get from the bottom to the top, right, and it's 2 to get one way, and it's 3 above that, well then the other one's 2, and then 3, then 2, then the one which has larger degree from the bottom should be longer. I don't know. You could do what you're saying, make the length of the line. And that's probably actually a useful comment in terms of constructing them for yourself and making things pretty, is to have in your mind something about that, like the length, the degree of the extension being proportional to the length of the, see here. Oh, here's the picture for that one. Yeah. It's a diamond. Yeah. It is a diamond. That's funny. So there's the lattice of subgroups for D4. So you got all those subgroups of order 2 over the identity, right? There's 5 of them. Surely by the end of abstract, you got tired of this question. How many times did I ask about the number of elements of order 2 in Dn? The first time it was like, oh, this question. By about the 4th time I've asked it, it's like, really? Again? Enough. But, there's all of the other people who didn't get it the first 4 times, so, I have to keep asking the question until they realize it's a question I'm going to ask. But anyway. And then those are the subgroups of order what? Well, R is cyclic, order 4, right? And I forget what those are. What are those things? I think those are Klein 4 groups. I think anyway.
You mean the ones to the right, not to the left?
Yeah. Because R squared has order 2, RS has order 2, and R cubed S has order 2, and RS. I think it's got 3 elements of order 2. So the interplay between these diagrams again is that this is the fixed field of what? That. This is the fixed field of that, right? r and all of its powers, they all fix I, and they mess with the fourth root of 2, and it's, it's corresponding roots to that minimal polynomial that takes the fourth root of 2 as its 0. And again, this is the fixed field of that. So, but he so he looks at these two and he says, well, what properties do those have to have, And that's down here, and he kind of walks you through how to figure out what those are. So, all right, I'm going to stop. All right, so so I'm at the moment skipping past sections. Let's see here. Oh, actually, I'm skipping past section 14.3, which is on finite fields. All right, which is it's just a short section full of quite interesting things. He actually sketches some sort of algorithm. He says, here I'll read you the paragraph on page 587, which is intriguing. He says, this gives a method for determining the product of all irreducible polynomials over Fp of a given degree. So you can build some sort of uber polynomial, which is a product of all the irreducible polynomials of a given degree. There's some method to create a polynomial of whatever degree is necessary over Z3, for example, which contains all of the irreducible quadratics as factors.
Does he mean an efficient method, or just a method? Because you could do it by brute force.
Well, here's the proposition 18. X to the p to the n is precisely the product of all irreducible polynomials in Fp of x of degree d, where d runs through the divisors of n.
So,
and then he says this proposition can be used to produce irreducible polynomials over Fp recursively.
so you just the product of them is just x to the p.
So, for example, here, let me write it out again. All right, fine. I guess I'm covering 14.3. You happy? All right. You guys are sneaky. X to the p. I guess I walked into this one. X to the p to the n minus x is precisely product of all distinct irreducible polynomials in Fpx of degree d, where d runs through all divisors of n. So here's an application of that proposition. Again, this is section 14.3. He says, look at this. If we look at x to the fourth minus x, all right? So that would be, so here we're looking at p. P equals to 2, n equals to 2, right? So it's not, so let's see here. The product of all distinct irreducible.
That includes just x itself.
Right, well, that's, no, but again, is the product of all distinct. Yeah, that'll also, exactly. So that would also include what? Any linear factors, right? So those we'd like to get rid of if we want to discover the quad. So that's, he's not saying that that is what I claimed it was. This polynomial is not the product of the irreducible quadratics.
Oh, okay.
In fact, there's only one irreducible quadratic over Z2, right?
Right.
How to discover that here? I mean, the theorem, you're right, the theorem includes this D could be what? 1 or 2 for us here, right? So to get rid of those, divide by x and x minus 1. Those are the irreducible linear factors over Z2.
Oh, right.
And so this is what? This is x. Well, I mean, we can use long division, right? Or whatever. How do you want? Here, I'll make my life easier. This is x cubed minus 1 over x minus 1, right? Which is x minus 1 times x squared plus x plus 1. Or x minus 1, which is x squared plus x plus 1. There you go. That's the sole irreducible, quadratic in Z2x, yeah? You guys got me. You hooked me. All right, I'll think about this section for a few more minutes. P equals 2, n equals 3. What does that look like? Yeah. So we're looking at apparently x to the 8th minus x, right? And again, product of all the distinct irreducible of degree d divisors of n. What are the divisors of n? 1. No, n. N is 3 this time.
Oh.
1 and 3, right? So if we want just to look at the irreducible cubics, we just got to get rid of the x and the x minus 1 factor, right? Right, yeah. Oh, that's kind of nice. Right? If you want to count the number of irreducible...
Yeah, didn't we have a problem on that?
Ooh.
421, where we had to find all the irreducible cubics in D2. And we just ran.
Yeah, but we were working, we did not have the machinery that we have here. I mean, like if I wanted to find how many irreducible polynomials of degree 11 over Z2, if I use this proposition, I got
You would still just have
2 to the
2 to the 11.
11th.
And then you
So 2 to the 11th minus 2 is the number of irreducible polynomials of degree 11. Oh. So I still, yeah. Oh, divided by. So divided by what?
Yeah, so that's 186
Oh,
irreducible. That's really cool, actually.
Degree 11 in Z2x. Yeah, because there's always, for a prime, if P is, well, and this is for prime, right? I think P is assumed to be prime in this proposition 18. But this one is here, this one's still manageable, right? This is, what is this? This is, I mean, I guess I'm going to go to long division because I'm lazy. There may be, maybe I'm not being lazy enough, actually. This is x squared minus x, so you get x to the 6th, right? Oh, that's x to the 7th minus x. X to the 5th. Oh, I think this is... So is it... Okay, fine. I think I see the pattern. All right, fine. So this is equal to x to the 6th plus x to the 5th plus x to the 4th plus x cubed plus x squared, I think. How does this story end?
I think it's plus x plus 1.
Yeah. There better be a 1 there, right? Otherwise, That would be troubling. Yeah. And then this is 6th order, and so it has to be the product of two irreducible cubics. I believe x cubed plus 1 is one of them. Oh, I'm wrong. Yeah, it can't be that, because if I plug in 1, I get 0, right? And cubics, if they have a 0, they're reducible, right? X cubed plus x squared plus 1? Plus x plus 1. That seems right. I mean, I worked these out explicitly just by, you know.
I was thinking, oh.
Well, this is definitely one of them because it has no 0.
Oh, it is.
Right? What's the other one then? Well, I mean, not up for grabs, right? There's an x cubed here. And there's got to be a 1 over here. So the question just becomes what to put in the middle. It's x squared. I think that makes sense. Then you've got the x to the 6th. We've got the x to the 5th. We've got x cubed. We've got x to the 4th.
Oh, right. Because you can't have 4 terms because then there would be a 0.
I mean, looks like we've got some extra copies of x cubed, but I think we've got an odd number of them, right? Because you've got this x cubed, that x cubed, we have 3 x cubes, which just gives us that x cubed. So that's okay. Yeah, there you go. Now, you said, now your question, Sam, was, does this give us an efficient method of finding the irreducible polynomials of degree whatever? I mean, that depends on how efficient you are at long division, I think. It's easy enough to find one of them, right?
I think.
Because if you, I mean, this is sort of the, I would say it's a generating thing, but it's kind of the opposite. I mean, generating things, usually you build power, you like take powers of something to build up something.
Yeah.
This is already got every single stupid the irreducible cubic in it, right? The question is just finding them.
Right.
So
it's long division to get rid of the things you don't want, but then it's just factorization to find the things that you do want.
right. So if you can,
Factorization is not efficient.
if you can find one, then you can split it off, and whatever's left is the rest. I mean,
No, but I think
Yeah.
factorization is technically a problem.
so yeah. And now he says there exist efficient algorithms for factorizations of polynomials mod p,
Oh, my.
which give the individual irreducible polynomials. See the exercises. But the importance of having irreducible polynomials in hand is that they give representations of the finite fields, f, p, n, as quotients of irreducible polynomials of degree n, which is conductive to explicit computations. Yeah. And then he gives an example of that. And the last page in this section is about the Mobius mu function, which is near and dear to these creatures called number theorists. Let's see here. We have one of them in-house. Ask him about that. It's not, you start talking about these sorts of things. Section 14.4 is on combining extensions, composite extensions. Section 14.5 is on cyclotomic extensions and abelian extensions over Q. I have given example 1 in section 14.5 as a test question last year. It went badly. But it shouldn't have, because we actually spent like a whole class period working this out. It's probably worthwhile to start down that path. So this is example 1 in section 14.5. Just flipped. Where'd it go? So here, looking at Q adjoin the 5th root of unity. All right. He says this is Galois over Q with a Galois group Z mod 5Z, the units in there, which is isomorphic to Z mod 4Z. So why can we say that? So I mean, he's claiming. I mean, how do you want to understand? How would you figure out that this is a Galois extension? So x to the fifth minus 1 takes as root. Okay, but how does that prove anything? What can you tell me about that polynomial, x to the fifth minus 1? It's separable?
Because it has one root in Q and the other four not.
Let's see here. Well, x to the fifth minus 1 is what? It's x minus 1, right? Times x minus the fifth root. Let me give this thing a name. Say theta. Minus theta. X minus what? X minus theta squared. X minus theta cubed. X minus theta to the fourth. Yeah? I can picture them. Right, here's that, and then I think theta's like here-ish. If I could, I don't know, they're two conjugate pairs and just the unity itself. Those are the fifth roots of unity.
So we can send any of them except not one to any of the others.
Right, the point is that if you have a field which includes the primitive fifth root of unity, since it's a field, it also includes everything else, which means that this is in fact a splitting field for this polynomial. And if it's a splitting field for the polynomial, it's certainly Galois.
But they're all primitive because it's the fifth root.
That's also true. Everything here is a primitive root of unity except for 1.
So that's why it's the group of units. Oh, it would be the group of units anyway.
Yeah, that's why there's the theta, theta squared, theta cubed, theta to the fourth. These are all primitive fifth roots of unity. Yeah. He says this is our first example of a Galois extension of Q with degree 4 with a cyclic Galois group. And the elements of the Galois group are, let's see here. I think he says sigma 2, what do you want to do with that one? Is take the fifth root of unity and send it to what? Fifth root of unity squared. He says since 2 has order 4 in the Z mod 5Z units. So is that not up for grabs? Like, could we send the fifth root of unity to the cube?
Yeah, we can.
That also has order.
Because if you send it to, if you take sigma 2 to the fourth power, that maps theta to theta cubed, I believe. Yeah.
Hmm.
Because it maps it to theta to the eighth, which is theta cubed.
Theta to the eighth is theta cubed, right? Let's see here. So he says there's precisely one non-trivial subfield, the quadratic extension of Q, the fixed field of the subgroup 1 and sigma 4. So he's calling the elements of the Galois group sigma 1, sigma 2, sigma 3, sigma 4.
And sigma 1 is equal to 1.
Yeah, sigma 1 is equal to 1, right? So Galois group. So what's the subgroup? Let's say H. 1 and sigma 3, is it? Or sigma 2 squared, I suppose. What?
Sigma 2 to the 4th.
Sigma 2 to the 4th, you say?
Is equal to
Sigma 2 to the 4th. I don't know, it's messing with me. Shouldn't that just be... Shouldn't anything to the 4th be the identity here?
It's sigma 4.
What's that?
I think it's
Sigma
sigma 4.
4.
Sigma 4 squared would be zeta. I mean, sigma 4 squared.
I guess my question for you guys is, what I don't know yet is, what is sigma 3?
Yeah, sigma 3 is equal to sigma 2 to the 4th.
How are you defining the sigma 2 and sigma... How are you defining the sigma 3 and sigma 4 is really my question.
Right.
That's what I'm missing.
Sigma 4 is sigma 2 squared.
So you say sigma 4 is sigma 2 squared. And sigma 3 is
Sigma 2 to the 4th.
sigma 2 to the 4th?
Yeah, because that maps. Wait, no.
I mean, simply.
No, that's wrong.
Sigma k is of zeta 5 is
Yeah,
zeta
no.
5.
Oh, it should be sigma 2 cubed. Sorry.
Sigma k of zeta 5 is what?
It's just the zeta 5 to k.
That's your guys' definition?
Yeah, yeah, yeah. But sigma 3 should be sigma 2 cubed. I was wrong.
Yeah, I can't, see, because it doesn't, I mean, this is a group of order 4.
Right.
So any element, any group element to order 4 has to be the identity.
Yeah, you're right.
By
That
like,
was-
you
that
know,
was dumb.
I mean, I've said plenty of dumb things today, so. What did you just tell me here? I've lost it already. Cubed, yeah. Let's see here. So there's a subgroup of order 2 here, right? Which is what? What has order 2? It should be sigma 4. Yeah, sigma 4. Because that is sigma 2 squared, and sigma 2 squared squared is sigma 2 to the 4th, which is the identity, because it's a group of order 4. And then but here's the interesting thing is, great, that's a subgroup of the Galois group. What's the corresponding fixed field? Right? What's the fixed field? I mean, it's a cyclic group of, it's Z4, right? So what's the, if for last semester we do Z4, the lattice of subgroups is kind of boring, right? 2Z4, right? 4Z4, also known as 0, right? So here you go, lattice. So, you know, great. We've got the Galois group. And then under that, but what's the the corresponding field diagram?
Q zeta 5. I mean,
Right.
the first thing is Q zeta 5, and down there's intermediate one, so Q zeta 5 plus zeta 5.
So here we have what? 0, right? H as I'm calling it. And then the Galois group. Am I doing that right? Zero should be 1. Yeah, you're right. Galois group of this thing. So what's the fixed field here? How do you find that, right?
That is a general pattern of things that we call zeta versus zeta.
Oh no, I am so sorry. Oopsie. You didn't hit record. Stop it.